This is geometry lesson 3-4, perpendicular lines. The perpendicular bisector of a segment is a line perpendicular to a segment at the segment's midpoint. And the shortest segment from a point to a line is perpendicular to that line. The fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. So just remember that the perpendicular line is the perpendicular segment is the shortest segment from a point to a line. All right, let's try that. Name the shortest segment from point A to line BC. Well, A is here, BC, so the shortest one would be the perpendicular one, so that would be AP. All right. Write and solve an inequality for x. Well, we've got this and this. Well, we know x minus 8 has to compare to 12. Well, if 12 is the shortest, then x minus 8 has to be greater than 12. Then we solve it, add 8 to both sides, so x would be greater than 20. All right. Perpendicular, or shortest segment from point A to line BC. Well, the perpendicular segment is AB. Okay. And then write and solve an inequality for x. So we're going to compare x minus 5 to 12. Well, x minus 5, AB is the shortest, so that has to be less than 12. So to solve this, we're going to add 5 to both sides. So my inequality would be x is less than 17. All right. Okay. There are 3 perpendicular line theorems that we use to prove lines, 2 of them prove lines perpendicular, and then the final one proves lines parallel. These are on page 173 in your book. I also have them on, I will be giving these to you for the quizzes and for the assignments and stuff like that in the Moodle notes section, so you can go ahead and look at those. And when you're writing these, you can just put 341, 342, 343 because they are kind of long going through them. All right, let's talk about them. 341. If you have 2 lines that form a linear pair of congruent angles, then the lines are perpendicular. So if you got 2 lines and you know that those 2 angles there are the same, then you got yourself perpendicular lines. So L would be perpendicular to M. 342, the perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of 2 parallel lines, then it is perpendicular to the other line. So if you know that you have 2 parallel lines cut by a transversal and one is 90, then this down here also has to be 90. So Q and P would have to be perpendicular. Those would be corresponding angles there because they'd all be 90. All right. 343. If 2 coplanar lines are perpendicular to the same line, then the 2 lines are parallel to each other. So this is kind of like the converse of corresponding angles. But if you can show that those 2 are both 90, then R and S would have to be parallel. So the first 2 prove perpendicular. The final one proves parallel. So write a 2-column proof, 4 steps. Here we go. All right, so we've got our givens. And we got 4 steps. We're trying to prove R is perpendicular to T. And then our givens would go there. So we're proving what we know. So R is parallel to S, and 1 and 2 are the same. All right. Well, if these are parallel, what kind of angle pair are 2 and 3? Corresponding angles. So we know 1 and 3, or 2 and 3 are corresponding angles. So now we just showed that those 2 are the same. Well, if 1 and 2 are the same and 2 and 3 are the same, don't we now know that angle 1 is congruent to angle 3? Having trouble writing here. That is by the transitive property. Okay? So then we got to go prove perpendicular. So we got to think back to our other page there. Well, we just showed that those 2 angles right next to each other are the same, so that would have to be 90. So 3, 4, 1 would be that proof. I think I've got it on the next slide here. Yeah. All right, so we had our givens, corresponding angles, transitive property, and then that would be the same as 3, 4, 1. you can just put 3, 4, 1 or whatever one that you use. All right, 4-step proof. Let's try that again. Write a 2-column proof, 3 steps this time. So we've got our given statement. 1, 2, 3. All right, this picture's marked up, and then we're trying to prove that this would come last here. We're trying to prove that those two are perpendicular. All right, so, well, what kind of angle pair are those two? Alternate interior angles. Well, we know they're the same because we were given that information. So if they're the same, wouldn't those two lines have to be parallel? So we could say EH, I'm sorry, I'll write that over here. EH is parallel to FG. Now we're proving parallel, so by the converse of alt int, converse of alternate interior angles. Well, that proves those two lines parallel. Well, if these two lines are parallel and this is 90, this also has to be 90, and that is the perpendicular transversal theorem, or 3, 4, 2. All right, it's kind of messy, but let's hear this really cleans it up. So we have our givens. Converse of alt int, they broke up the givens. We can put them all on the same line. Doesn't matter how you do it. And then the perpendicular transversal theorem, or 3, 4, 2. All right, so use those 3. You got that those note sheet to do that. There you go. A carpenter's square forms a right angle. A carpenter places the square so that on one side is parallel to the edge of a board, and then draws a line along the other side. Then he slides it down and draws a second line. Why must the two lines be parallel? Well, 90, 90. What kind of angle pair are those? They're corresponding, okay? Or they're both perpendicular, which means those two lines have to be parallel. Two answers work here. Converse of corresponding angles, or 3, 4, 3, because that is the only one of those theorems from today that proves lines parallel.